Okay, good morning also from my side. I hope everyone had a good evening yesterday. I had it. It was very talkative, very collaborative here. I really enjoy the mood that's here. And I can give you the first speech today about our activities that we are really currently having to use gallium nitride in traction inverters. My name is Katharina Berberich. I work for AVL. AVL is a big Austrian company. We are mainly a technology provider. Many of us know us also for our test stands and test equipment for the automotive world. And we have a department taking care of simulation tools and simulations, and another department that is solely focused on engineering services, and that's where I'm from. So we are not a tier one. We are an engineering service provider. We do in-house own developments from time to time or regularly in order to be able to provide our customers concepts, understand the technology, bring the technology forward, have development platforms, this kind of things. But our main business is really to customer-specific projects, and then the IP is owned by the customer. So we are very often more in the background as other engineering service suppliers as well. But we are doing this since 1948. So, one of the things we are doing in-house at the moment is looking at gallium nitride for traction. And I can show you today where we stand there. So just a short overview of the whole power stage R&D activities around wide bandgap that happened. Gallium nitride is not new in automotive. It's used in onboard charger and DC-DC now since a couple of years. There has been a lot of R&D investments already. And I guess in general you can say it's known how gallium nitride can be used in this kind of applications. This kind of applications do not have a very high power consumption, so there were always GaN devices available that could fit, or that did fit. The limit was on the power, on the maximum current of the GaN devices. That's why it did not immediately make its step into the traction inverters, because here we need much higher currents, 300, 400, 500 amps. And there was, at the time, around 2020, there was just no solutions available for this. There needed to be done developments on the process side for the semiconductor suppliers, for the module development. And this happened in the background, at least for us in the background. And now the first solutions that are capable of higher power are starting to become available. So that's still early stage. At the moment, state of the art in traction inverters is really silicon carbide. Silicon carbide is everywhere, still together with IGBT. But everybody, I would say, knows how to do a silicon carbide inverter. That started, the R&D investments there started around 2018. The main driver was to get the efficiency up, get some additional advantages on power density, and it came with a cost adder, a quite significant cost adder. So back then, we always took the calculation to the system level, and then we said, on system level, it really makes sense because it can either bring the cost down for the batteries and it leverages out, or it just helps to get higher reach, which is important for the customer. So many companies decided to make this move to silicon carbide, knowingly that it's expensive. Since then, cost pressure has risen extremely. So a couple of years ago, the concepts of hybrid power stages came up using silicon carbide and IGBT in parallel. With that, bringing the cost down, obviously, but then also bringing the efficiency down a little bit. And the goal was to find the sweet spot where I already have a significant cost reduction, but the efficiency is just a little bit. So I'm taking this as a good compromise in a cost-driven environment. But it's a compromise. And now comes GaN, and GaN can bring the cost down again, and with absolutely no compromise on the performance, on the efficiency, power density, this kind of things. That's why we think that's really, really interesting technology. Here is the summary of the topic that can be addressed to this. Cost. I'm writing here what's prognosticated to be true in the future, that will have a price tag comparable with IGBTs. Yesterday there was a presentation from Matthew, who made a question mark there, because yes, it's correct, at the moment it's really difficult to look into the future and predict this. And I also know that there are people in here, and I have talked to people who are fully convinced that silicon carbide will have the same price tag in the future. That still needs to prove if it's true. One thing is clear, this price tag will come out of China. And combining this with a good de-risk strategy, and the fact that silicon carbide needs more power during the production process than GaN, that's a fact. And the higher availability, every silicon fab worldwide can be, brought up to speed to be able to produce gallium nitride. It's a valid point that makes it worth really to look and investigate into gallium nitride. And this goes together with the other topics around efficiency. That's really important. That's really good here for gallium nitride, and general performance like power density and faster switching. So when we started to investigate GaN, we were, like 2 years ago, we were particularly interested to understand the efficiency situation. Though we looked for a power stage, not too much available at that time, we found one at we.CONECT. It's using 650 volt switches, so it's a 400 volt system, 330 amps RMS in a power module, classic 2-level topology, 3 phases. We took this power stage prototype, combined it with our control board and control software that comes out of our inverter development platform, connected it to a 3-phase PSM e-motor and put it on the eDyno to do the efficiency measurements. This is showing the efficiency map we had at the end, and in that efficiency map there's a maximum efficiency point of 99.67, and that's really good, good result for the overall efficiency. Important are some parameters we took here that are related to the switching losses. And that's, we choose a switching frequency of 10 kilohertz, and a slew rate, and that's the switching speed of the PWM, of around 13 kilovolt per microsecond. That's not yet stretching the capabilities of GaN. But we used these numbers so we could repeat the same operating point with a state-of-the-art silicon carbide 400 volt system and make a direct apple-to-apple comparison. And that comparison is done on a WLTP level. The numbers are shown on the slide here. The numbers that you are seeing are energy consumption. And then we put this always in relation to silicon carbide as the base in percent. So the delta in percent is related to silicon carbide. So a negative number means gallium nitride has less power consumption. Positive number means it has higher power consumption. The average is, I think the number is 0.23, which I would label as comparable. It's not a big advantage, and also not a big disadvantage. It's really comparable. The more interesting is when we dig down into the different phases of the WLTP that correspond to different driving scenarios. There are 4 phases in the WLTP that are shown here. 0 is the silicon carbide again, that's the baseline. And then the negative values are good for gallium nitride. And we can see that particularly in the lower 2 phases, which correspond to urban, lower speed driving environments, the advantage is really visible, the efficiency advantage. And then over the other phases in the average, it averages out. So it means for us that gallium nitride is absolutely, comparable to silicon carbide, and even has advantages when you go into the smaller vehicles, the urban car kind of concepts. After these measurements, we decided measurements are good, but we want to see this really on the road. We want to see how it behaves in the real automotive environment, driving in a demonstrator car. So we sat together with we.CONECT and decided to start a development project of a, let's say, real inverter that we can put into an e-axle and into a vehicle. So the question, of course, came up, and I've summarized this here. What's the difference when I want to do a gallium nitride inverter versus the SiC inverters I've done the couple of last years? And this is how we approached it. So in theory, you can increase the slew rate, but we will not do this, or we have not done this. We will stay below 20 kilovolt per microsecond. And the reason is the e-motor, because this really stresses the e-motor. We will have increased bearing currents. If we go higher, that destroys the bearings. We will have, issues with the isolation of the windings. This all relates to lifetime and reliability, and we just decided that we will not stress this point too much. Going close to 15-20 is already a step, but we will not stress it more. What we want to stress is go up with a PWM output frequency, because this is also possible with gallium nitride modules, and this will allow us a new freedom in the range of the software development, software controls development, optimized pulse pattern, and this kind of things. And that's where the focus will be. There's another interesting point about GaN, and it has been touched yesterday. There's not just one GaN switch solution out there to semiconductor suppliers. So when you search, you will find that several are doing GaN, and they have different methods, and that requires different gate drivers. So very often the module comes with a specific gate driver to drive it, and you can't easily switch it, have one new gate driver design and then switch the power modules, as it was possible with SiC and IGBT. So there's much more. Maybe there will be a consolidation in the future. I don't know. At the moment, I don't see it. So there's really more the couple thing on gate driver plus power module that needs to be evaluated, that needs to be considered when you do second source or scaling programs. What stays the same is how important it is to do a low inductance commutation cell design. So next page shows the parameters of the inverter we have developed. 400 volt system, 650 volt switches, 500 amps RMS. That is achieved still with parallelization of 2 power modules. We are using the next generation from what we did for the efficiency testing of we.CONECT. So these are now transfer mold semiconductor half bridges, which are shown in this rendering here. So this is a technology that's capable of being brought into SOP. It's not a prototype-ish power module anymore. We need to do the parallelization. That means this is a dual inverter, so each stage has 6 of these half bridges. We got the gate driver that's developed by NXP specifically for this power module. It's, besides the fact that it can drive the specific module, it has all the other newer next generation gate driver features that we have seen the couple of last year. One of them is, and that we are planning to use already, is the adjustable slew rate control. Then it has a common DC link. Ultra low inductance design, I mentioned it, of 7 nanohenry, and it will be an inverter that we call it semi-integrated, or it can be integrated on top of the dual e-motor e-axle. It has 2 control boards, so we can also do torque vectoring with it. And this is the technology demonstrator e-axle. It's shown here. It's a real, it's a real picture of the axle we have. So it's, besides the dual GaN inverter I already showed, it's 2 PSM e-motors, 30,000 RPM, oil-cooled, and with hairpins. So state of the art. The switching frequency for the very, very first bring up, we will stay with 15 kilohertz and integrate it directly into the Tesla demonstrator car. It's a Model S that we have. The demonstrator car is currently driving around with an 800 volt silicon carbide e-axle in the exact same form factor. We just scaled it down so we can even replace it. We can have the demonstrator car run with the 800 volt SiC or with the 400 volt gallium nitride. And then the next step, what we want to do is, once this technology is on the road, we will bring it into a more SOP targeting development platform. So the target of that design is then really to be able to use it as a starting point for SOP designs. It'll be a single inverter standalone that can be integrated with various e-motors. It'll probably drive a PSM and FSM as a modular design. Switching frequency we want to bring up then to 50 kilohertz min. We will see how high we can get and how high will make sense. And then also integrate it in a different kind of smaller vehicle demo car. And we could not have done this without our development platform. And it has been discussed yesterday a couple of times, the need for speed in the developments and also specifically in the R&D topics. So this development platform really helped us to get this technology demonstrator up and running with not too much budget, because we are really taking something we are having, a modular design, and just replacing the power stage and scaling it, and also in a reasonable time frame. So this development platform I want to show, we started this in 2020 with 800 volt silicon carbide. Turnkey complete inverter development was intended for this e-axle I shortly mentioned that's driving in the demos in the Tesla at the moment. Afterwards, we quickly spun a single version out of it, standalone, for testing purposes, customer projects, this kind of things. Then we had a platform where we could work on the application software, make it AUTOSAR, model-based design, add additional functions. From time to time, we can go and make a small data validation, put it in the demonstrator car again, have the test results. And we also saw that it's really necessary to have the platform to be very modular, to use it for this kind of applications and also for our customers, because the whole powertrain development has changed. Very often people want to own the software but don't need to own the hardware. Somebody only needs the control board with BSW but wants to do his own application software. So there are all kind of variants out there. Therefore, this was really put into make sure that it's modular, usable, specifically the application software only, control board plus BSW only, hardware only. And then this is also what we did here for the we.CONECT. We call it we.CONECT internally, but it doesn't really have a number yet. The 400 volt GaN dual inverter design, where we took the mechanic design we had, we took the control board and the software and just replaced the power stage and the gate driver, actually. And need some updates on the software, but that's it. The rest is a takeover. In parallel, we are working on bringing the control board to a next generation control board, next generation microcontroller like a TC4X that has a hardware accelerator. Then there's a project ongoing that we call FOC 2.0, which is basically a software architecture change, because in order to fully utilize this new microcontrollers, there needs to be a change in the architecture. Otherwise, we can't fully utilize this additional cores that are integrated, like the hardware accelerator or the DSP. And then there is a multi-level power stage ongoing in a European Union funded project called High Power 5.0. There we will only do the power stage first, And we will also look into using bidirectional GaN switches in the T phase of it. And then hopefully afterwards will be time for this platform design that I also showed. Because it's not enough yet, what's happening in the powertrain, there's this completely new powertrain architecture coming up that has also been touched yesterday. There's no standalone inverter anymore. Everything is integrated in the battery. You have a battery, you have a matrix set up and can directly drive the inverter and also onboard charger DC-DC functions out of this new smart battery. So we are also working on that and should have a demo or technology demonstrator in 2027. And then we'll see what happens in the future, but we are fully convinced that the standalone inverter R&D and investments will continue and will be used in vehicles. And that's the summary slide. Once the GaN for high power traction is available, it's a platform, and the real beauty of gallium nitride is that not only the cost point, it's really that it opens up a big room for innovations. Because now you can bring the switching speed up, and now you can think about what to do with it. You can have additional or new control strategies, optimize pulse patterns, has an effect on a lot of system parameters like NVH, bearing currents, efficiency, everything around that, predictive maintenance, software functions. We have discussed with companies and also startups who are working on completely new e-motors, and some of these e-motors need a higher core or PWM switching speed from the start. So this is also enabled by gallium nitride. And then, of course, what I mentioned at the beginning, just the urban vehicles with higher efficiency at similar cost, or with no additional hardware costs. So it's really all in the software, and there's really a lot of room, and I'm really excited to see what's going to happen in the next couple of years when people start to play with these traction GaN inverters. Thank you.